Welcome back to calculus. Welcome to section 3.2. So we know chapter 3 is all about applying the derivative and all these different things that we can now do with derivatives now that you guys know how to differentiate or find a derivative. Today we're going to be talking about Rolle's theorem and the mean value theorem. Let's start by chatting about Rolle's theorem. So in yesterday's lesson, what did the extreme value theorem actually state? And by yesterday, I mean last week's lesson. What did the extreme value theorem actually state? Well, it told us that a continuous function on a closed interval from A to B must have both a min and a max somewhere on that interval. And again, this closed interval, like that was really important, right? We had to deal with some of those endpoints. So where could these special points, this min and this max, where could those be located? Well, we talked about these fancy things called critical numbers. And what we were doing last week on Thursday, we said, well, the min or max could be located at the endpoints. We had to also check our endpoints. Rolle's theorem, named after Michel Rolle, gives conditions that guarantee the existence of an extreme value in the interior of a closed interval. So let's actually get into what is this Rolle's theorem. So it is theorem 3.3 in your textbook. Again, I'm going to make sure that f is continuous. I'm going to be looking at this closed interval. But now we're saying f is differentiable on this open interval if those two things are true. So continuous, again, that just means like no gaps, jumps, holes, things like that. Differentiable, it's simple here the way I'm going to say it, but basically I can take the derivative at all points. So I am able to take the derivative. That's what I mean by differentiable. And there is a difference here. So continuous on the closed interval, differentiable on the open interval. I'm not saying I need to be differentiable at the endpoint exactly, okay? If those things are true, and if f of A equals f of B, so think about plugging in A and B and them both spitting out the same thing, then there's at least one number, C, in this interval from A to B, such that the derivative, when you plug C in, is going to equal 0. So cool, but what does that mean? Okay, so here's a visual representation of Rolle's theorems. Basically, what we're saying is I want my start and end points to be at the same point, same height. If that's accurate, then I know I must have a horizontal tangent line somewhere in my graph. So if those requirements of, again, continuous and differentiable, if those requirements are met, there must be at least one x value, we're going to call it C, between A and B, where the graph has a horizontal tangent line. So think about connecting these two dots here. Well, they're connected by a horizontal tangent line. If I know that my function could be doing absolutely anything between those two lines. But since I know that my two dots, where x equals A, where x equals B, those are at the same height, then I know for a fact at some point my function is going to have this horizontal tangent line somewhere. And there could be multiple points, all right? I could have two dots here, right? If I know that my function is continuous and differentiable, well, maybe it's doing something crazy like this. But if these two are at the same height, I know, hey, here's a horizontal tangent, here's a horizontal tangent, here's a horizontal tangent. You guys kind of see what I mean there? That's what Rolle's theorem is all about, all right? We're going to have to be checking these conditions as we start doing some of these problems. Here's another visual. So what happens when the differentiability requirement is dropped? Again, differentiability in a very simplistic way, but basically, can I take my derivative at all points? I am not a differentiable function when I have something like a point or a cusp. So something like this point right here, it would still count as a relative maximum, but it is not a horizontal tangent. So at a discontinuity, we may have a vertical tangent line. We have, or I guess I should say we might have a vertical tangent line. So this still represents a critical number. but it's just not a horizontal. So no horizontal tangent. And if that's the case, then it means there's no place where our derivative of x equals 0 between endpoints. So we have to make sure that our functions are differentiable in order to apply Rolle's theorem. All right, let's actually get into an example here. Find the two x-intercepts of f of x equals this and show that f prime of x equals 0 at some point between those two x-intercepts. So the reason why we're doing this with x-intercept is because they both must spit out the same y value, right? So for example, if I have this x-intercept and this one, well, they're connected by a little horizontal line. So no matter what my function is actually doing between those 2 points, I know that Rolle's theorem is going to have to work, okay? That's just a random example drawing. That's not actually what this function looks like. So let's actually do this problem. All right, to find x-intercepts, I need to set y equal to 0. 0 equals x squared minus 3x plus 2. Let's go ahead and factor that out. That's going to be x minus 2 and x minus 1, which means x should equal 1 or 2. So my two x-intercepts are going to be 1, 0, 2, 0. All right, those are my x-intercepts. So there must be some point in the interval from 1 to 2. Now, this does not represent a point. This represents an interval. There must be some c value between 1 and 2 such that my derivative, when I plug c in, equals 0. Let's find that derivative. So f prime of x would end up being 2x minus 3. And here we're going to set that equal to 0. I'm going to come over here. 2x minus 3 equals 0. And let's just go ahead and solve this thing out. We're going to end up getting x equals 3 over 2. Is that between 1 and 2? Yeah, okay, 3 over 2, that's 1/2. That's right between 1 and 2. Cool. So that means this is the value that satisfies Rolle's theorem. C would equal 3 over 2, or 3/2. All right? So that's one possible example. Again, here we just did intercepts because we know for a fact they're going to have the same height or the same corresponding y value. Here's what this graph would actually look like. So here you can see our 2 points, 1, 0, 2, 0, and then somewhere between there, I do have this horizontal tangent line where x equals 3 over 2. And you can always do this, right? Like you guys have graphing calculators, use them. Make sure that you're getting something that makes sense. All right, let's keep on moving on to the mean value theorem. So the mean value theorem, theorem 3.4, says if f is continuous on closed interval AB and differentiable on open interval AB, that's the same starting place as Rolle's theorem. Okay, so far we're the same. Then there exists a number c in AB such that this whole equation must be true. Okay, great, but what does this mean? So with Rolle's theorem, I said, hey, my 2 points, A and B, they have to spit out the same y value. They must be at the same height. Then I know I can set my derivative equal to 0. There must be a horizontal tangent line. The mean value theorem says, okay, what if I have a graph that looks, I don't know, something like this, let's say. I could pick a point here. I could pick a point here. Those clearly don't have the same y values, right? But let's say, okay, that's A, this is B. Mean value is saying there is going to be some x value, we'll call it C, that has a tangent line with the same slope as that which connects A and B. So I don't know, maybe that would be right here. Here it kind of looks like our tangent line. That tangent looks like it has a pretty similar slope to the line that connects our 2 points over there. That's what the mean value theorem is saying. Again, the easiest way to do this is let's do a problem or two, okay? Sometimes you will see this term secant line pop up. We talked about this a little bit at the end of the year. Secant line, that is what connects 2 points, or it passes through a function in 2 places. Your tangent line, again, just kind of brushes past at 1 point. So here we're saying the tangent at 1 point is going to have the same slope as the secant that's connecting your 2 endpoints. All right, let's do this example down here. Example 2, given our original function, here it is, Find all values of c in the open interval from 1 to 4 such that this whole function, this mean value function, must be true. For all of these problems, we would want to check and make sure that we are continuous and differentiable. For this one, we are going to assume that that is the case. Sometimes it's helpful to like graph your original function and see, okay, do I see any weird, sharp points or cusps or anything like that? You could always check it out. But otherwise, we're going to jump into this one. For your homework for the mean value theorem, I do actually want you guys to like pause for a second and think, okay, do I think this is continuous? Are there any like glaring holes or jumps or gaps? Do I know of any sharp points? Like for instance, if you're ever dealing with like an absolute value, well, you know that the graph of that has this sharp point somewhere. That's not going to be differentiable at a certain point. If this point is somewhere in the interval that they're talking about, I couldn't apply the mean value theorem. Okay, that'll show up in your homework, all right? Anyway, but for this one, we're saying she's continuous, she's differentiable. Let's go ahead and plug things in. So first, let's find f of 4 and f of 1. We're plugging into our original function right now. So 5 minus 4 over 4, that's 5 minus 1, that's going to be 4. So this kind of represents this point 4, 4. Cool. And then we have 5 minus 4 over 1, or 5 minus 4, that's going to represent 1. So that's giving us this point where x is 1, we plugged 1 in, and we got out 1. All right, those are our 2 points. Now let's go ahead and use our slope formula over here. It's going to be 4 minus 1 over 4 minus 1, which is going to equal 1. Okay, that's the slope of the secant line that connects your 2 endpoints, slope of the secant line. What I want to do now is set that equal to my derivative. Our derivative for this problem, well, the derivative of 5 would just be 0. So I need to figure out what's the derivative of negative 4 over x. 4 over x. I can always rewrite that, right? So this original function is 5 minus 4x to the negative 1. So my derivative would end up being negative 4, and then pull down that negative 1, x to the negative 2. Okay, cool. I can rewrite that a little bit, and we end up getting 4 over x squared. Okay, so here's where I'm going to take these 2 components. I'm going to set them equal to each other. That's what the mean value theorem is telling us to do. And we're just going to go ahead and solve. I'm going to multiply both sides by x squared. That's going to cancel out over here. I'm left with 4 equals x squared. Take your square root. You're left with x equals positive or negative 2. When I'm taking a square root, right, I could have both of those be the answer. But here they're just asking us about this interval from 1 to 4. Only positive 2 is in that interval, so that means the c value we're looking for here would just be 2. That is the value that satisfies the mean value theorem. All right, so that's our answer for that one. I'm going to show you what this one looks like as well. So here you can see our 0.11, our 0.44. Here's the secant line that connects those two. And at this point where x equals 2, the tangent line has the same exact slope as that secant line. All right. I'm going to just show you an alternate form. Sometimes with polynomial functions, rational trig functions, they're always differentiable, right? So anytime you're dealing with a polynomial, rational, or trig, they're just going to be differentiable. So you can glance at it and you can say, oh, that's polynomial. Great, I know it's differentiable. Sometimes it is helpful to use this alternate form of the mean value theorem. All they've done here is they just rewrote it, okay? I could easily, subtract over the f of a and get f of b minus f of a equals b minus a f prime of c. I could divide out by that b minus a, and boom, we're back to that original form that we started with, okay? So this is just an alternate form. Sometimes, depending on the question being asked, maybe it's helpful to use this form. Maybe not. Just jot it down. It could come in handy, depending on what they're asking you for, okay? Sometimes maybe they'll ask you something about an endpoint. Maybe this form would be better for that, but it's just an alternate form. Most of your homework problems today, we're going to stick with the regular one. This alternate might pop up in a future day or two, okay? All right, our last example here is an application example. And this one at first is like, how am I using Rolle's theorem or mean value theorem? But stick with me. So I have two patrol cars here and here. They're equipped with radar. They are 5 miles apart on a highway. As a truck, this guy here, passes the first one, its speed is clocked at 55 miles per hour. 4 minutes later, when the truck passes the second patrol car, its speed is clocked at 50 miles per hour. Prove that the truck must have exceeded the speed limit, and we're saying the speed limit here is 55 miles per hour at some time during the 4 minutes. Okay. What I want us to think about here is how could I take the given info, the given data, and convert it into like points that I could apply this theorem to, okay? So we are going to let T1, our first time, our initial time, just equals 0 hours. That's when the truck passes the first patrol car, okay? T equals 0. 4 minutes later, I'm gonna have T2. I want this to be in hours for both of these though. So if they're giving me 4 minutes, I'm gonna quickly convert that by dividing by 60. That's gonna give me 1/15 of an hour. Okay, so that's T2, 4 minutes later, or 1/15 of an hour, all right? So I know T1, I know T2. You can kind of think about those as like X values, right? I have my two different times here. We're gonna go back to using S of T a little bit, but it's not gonna be exactly the same as the physics problems we did last time. We're just gonna remind ourselves, hey, S of T is our position function. And here I'm definitely dealing with position and velocity, right? Position and speed. I know that my position at time 1 or 0, my position is just 0. I'm passing the first patrol car, but I know my position when time equals 1/15. Well, I'm passing that second patrol car, so I must be at 5 miles. All right. So basically what we have here is we have 2 points. I have this point 0, 0, and I have this point 1/15, 5. All right. Again, these are time, and these ones represent position. And we use that S of T function for position. So then average velocity, well, that would basically be change in position over change in time. I'll write that out here. Average velocity is change in position over change in time. Kind of sounds pretty slopey to me. So I'm going to say that average velocity is the same as S of 1/15 minus S of 0 over 1/15 minus 0. This looks pretty much like that mean value theorem or like Rolle's theorem. I don't know. We'll see. We're going to plug in what we know. S of 1/15 is 5. S of 0 is 0. 1/15 minus 0. We end up getting 5 divided by 1/15, which when simplified gives us 75. Okay, so what is this actually telling us? This is telling us I have 2 points. I know that the slope between those points, which in this case represents average velocity, I know that the slope there is going to have to, like, I'm going to have some other X value that matches that slope, okay? So here, I'm going to finish this off, assuming the position function is differentiable, and we know it is. The position function is a polynomial. We may apply mean value theorem, or we often just call it MVT, mean value theorem here, to conclude that the truck at some point was going 75 miles per hour. Somewhere in that 4 minutes, all right? So I like this one because like I said at the beginning of it, I feel like it's completely different than some of the other examples that we've done. And I don't think many people would think about like a speeding ticket coming from calculus, but you can use calculus to determine if someone's speeding or not. I don't know if those cops are sitting there doing calculus, most likely not. But I just think it's kind of a fun application. So if you want to go back and watch any part of this again, just to clarify it, great. Otherwise, like, you guys have access to so many resources. Feel free to look up other videos for mean value theorem applications. Do what you got to do. Your homework does not include an application. Oh, no, it includes one application problem. Okay, one application problem in your homework. The rest are just straight up Rolle's theorem or mean value theorem problems like that. So finding your derivative, and then for Rolle, setting it equal to 0. For mean value, setting it equal to the slope between those 2 points. Here is your homework assignment. I did add a few more, because there weren't any mean value problems. I wanted to make sure that you had some practice with mean value. So feel free to get started on those. We will clarify anything that we need to clarify tomorrow. We will do some more practice with this. If you want to get ahead, read section 3.3. Otherwise, see you guys tomorrow.